In this lecture, we'll be talking about trends in entropy, continuing on our discussion of entropy from last time. And we'll also be introducing the third and final law of thermodynamics. And the title slide here will make a little bit more sense when I show the video clip later on in the lecture. Okay, so just to remind ourselves what we did last time, we raised this question: how do we know when a reaction is spontaneous? And then we sort of answered that with this concept of entropy and the second law of thermodynamics, and that is that the entropy of the universe is always increasing. So any process that increases the entropy of the universe will be spontaneous. Okay, and this second law of thermodynamics also brought up that concept of the heat death of the universe. That's sort of a consequence of the second law. Okay. Today what we'll be talking about, we'll start off talking about factors that influence entropy, and those are phase of your system, volume, molecular size, and temperature. And then we'll introduce the third and final law of thermodynamics, and that law states that the entropy of a perfect crystal at absolute zero is zero. Okay, so it's a little bit of a mouthful to state. Why it's important is because you can use this to calculate entropy for a given process. So you can calculate the entropy of a particular compound at a particular temperature. That's a ramification of the third law. That's why I guess the third law would be important to us. Okay. So we are still in the first section of chapter 20. We're going to be talking about the factors affecting entropy. Okay, and again, those are volume, phase of the system, number of particles, and temperature. Okay, we talked a little bit about volume last time. Remember the example of the piece of elastic with lines drawn on it that represent energy levels. As you stretch that a piece of elastic to represent an increase in volume, you see that more of those energy levels are available in a given area, shaded in yellow. Okay, I think that's fairly self-explanatory. The larger volume you have, the more the energy levels sort of, in this example, they get closer and closer together, and thus the more you have available to you. So the more microstates you have available. Okay. What about phases? Okay, and you might be able to kind of guess this, but the entropy of a solid is going to be lower, or the lowest of all phases. Then comes liquid, and then finally gas will have the highest entropy. Okay, and why is that? Well, it's simply the particle movement and motions. Okay, so in a solid, this is water for this example. The water molecules are fairly well ordered here in ice in the solid. Okay, as you go into a liquid, they're still pretty close together, but they are movement. There's a lot more movement in there. And then finally in a gas, they're very spread apart, and they're going very fast, and they have a larger degree of freedom. Okay, so water at room temperature, 298 degrees Kelvin. Liquid water, if we look at these examples here, liquid water has an entropy of 69.9 joules per mole Kelvin. Water vapor in the gas form, that is substantially higher, that entropy. Okay. And the difference in those would be the delta S for that phase change is 119 joules per mole Kelvin. Okay, and you can see that on this plot. So if we plotted temperature versus entropy, you can see that in the solid ice form, as we add temperature to it, the entropy increases as temperature increases. But then we get to 0 degrees Celsius, And you can see there's a large jump here, sort of instantaneously. What that is, that's a phase change, going from solid to liquid. You increase the entropy just for that phase change, so the temperature doesn't change, the entropy does, because of your changing phase. And likewise, from liquid to gas, there's this really big change there, which we saw as 119 joules per mole Kelvin. Okay, this is very similar to a plot we showed that we plotted heat versus temperature. This is a little bit different, but the similarities is that you have these big jumps from phase changes. Okay. And this same plot, just kind of another way to show it. I believe this is not water. This is a gas. Not sure what gas this is off the top of my head, but it looks like a diatomic gas, perhaps O2. Okay, as it's solid, right, going from 0 degrees Kelvin to looks like around 55 or so, I guess 59. You get this jump from going from a solid to a liquid. Okay, and then the same thing from liquid to gas, you get another big jump. Well, there's phase changes like that, we can kind of think about kind of easily, using water as a classic example, because we all understand the 3 phases of water, solid ice, liquid water, and then water vapor. You can have a phase change as well when you have something like salt, a ionic solid, and you dissolve it into liquid. Okay, that salt, that entropy of the salt is going to increase because now the salt, those ions, they're not in a crystal, a solid crystal. They can freely move around and interact with the water. So that is also an increase in entropy from mixing those two. And even if we mix things that have the same phase to start, like ethanol is a liquid alcohol, and water, both liquids, they both form hydrogen bonds with themselves in solution. When you mix them together, now they can kind of start interacting via hydrogen bonds with one another, and so that in itself makes more freedom of motion and more interactions, or microstates, if you want to think about it that way, and the entropy would increase with this mixing. And then finally, final example here of looking at phases of molecules. Gases can actually dissolve into liquid. So here we have O2 gas. In the gas state, it has a very high entropy, but it can also dissolve, gas can dissolve into water here. And when it does that, the entropy of the gas that's dissolved in the liquid phase is much lower. Right, so another trend that we'll talk about in terms of entropy is particle or molecule size. Okay, entropy increases as the complexity of the molecular structure increases. So if you have more bonds, more things bonded together, there's more opportunities for internal motion within that molecule, and therefore there are more microstates and more entropy. And this is illustrated here if we look at simple hydrocarbons. Probably the most simple one is methane. You have a carbon with 4 hydrogens, and its entropy is given here as 186. Well, if we add 1 carbon to that, so ethane, now the entropy is larger than methane's. Add another carbon to this chain, we have 270, and add a 4th carbon, again the entropy increases. So the more molecules, or excuse me, the more atoms we have in the molecule, the higher the entropy is going to be. And this table just kind of illustrates that as well. I should mention you don't have to memorize these values. All we're trying to do here is show you given a solid, right, a very basic solid like sodium chloride, its entropy is 72.1. Maybe make that a little bit more complex with aluminum trichloride, right? So now instead of just 2 atoms in our compound, we have 4. That entropy increases. And then something more complex still, this P4O10 has a higher entropy still. And then just contrast that. These are all solids. Contrast that with the entropies here of these nitrogen compounds that are all in the gas phase. Something like NO in the gas phase has a very similar entropy to a much bigger, more complex molecule in the solid phase. Okay, so gases, that's an illustration of how the gas phase affects this as well. Okay. And again, the trends for molecule size really only hold for substances that are in the same physical state. Because, like we just mentioned here, you take a very simple gas molecule, it can have a very similar entropy to a very complex molecule that's in the solid phase. In the complexities as we get larger and larger molecules, if we take these 3 and look at them in some more detail, right, NO, NO2, and N2O4, you see that the entropy increases. Well, the number of degrees of freedom, the way that these molecules can move in the motions available to them, you see how much it increases. So NO, if we're looking at vibrations here, it really only has this one bond, right? So it can only vibrate along this one bond. NO2 now has 2 bonds, so we can do some vibrations along both of those. And then you can also get some bending along both of those bonds. So you can see that the degrees of freedom, the amount of motion, or the number of microstates, however you want to think about that, that increases. And N2, that's a typo, N2O4 is greater still, right? There are many, many more motions in that molecule than these 2, which increases the entropy of that molecule. Right. So I want to introduce a term here called allotropes. And what allotropes means, it's a different form of the same element. So the easiest example here is for carbon, you can have 2 different allotropes, diamond and graphite. Right? They're both pure carbon, but they're very different in properties. Right, so diamond has a very rigid network of covalent bonds, which means there's less range of motion here, and there'd be less entropy when compared with carbon, the other allotrope of carbon, which would be graphite. Okay, there's covalent bonds within layers of this, but weak forces kind of connect the layers of these carbon rings together. Okay, so those weak non-covalent forces allow more flexibility and more range of motion within those within the structure of graphite. So it has higher entropy when compared with diamond. Okay. And the last trend we'll talk about in terms of entropy is temperature. Okay. And I think we mentioned this in last lecture, but entropy increases as temperature increases. You get an increase in kinetic energy. You get an increase the number of accessible microstates. Here we have, if you're just looking at following the motions of a molecule at lower temperature, this is kind of where that molecule would be, these molecules, I should say, would be kind of moving around. As you increase the heat and raise the temperature, you can see the motions go up. So there's more freedom of motion, more microstates, which would be a higher entropy at a higher temperature. And this is how you'd visualize that. It looks very similar when we plotted this in terms of volume. lower temperature, the plot here, the distribution is just a little bit more narrow on in terms of kinetic energy. When you increase that temperature, you might think it would go up, but it doesn't. It spreads out. Okay, and that spreading out means that you have a greater distribution of energy, a greater number of energy levels available. And probably an easier way, at least for me, to visualize this is, if you have a sort of well and you have certain energy levels available at a given temperature, as you heat it, the deepness of that well would increase, and as it increases in height, you're going to gain other access to other energy levels. So you just have more energy levels available. We saw a similar picture when we talked about volume to this, but when you increase the volume, you kind of just make this well wider, and that shrinks the gap between these energy levels, and some higher energy levels can kind of go into that well. In terms of temperature, you don't make it wider, you just make it taller. But you accomplish the same thing. You're making more energy levels accessible. Okay. So the reverse is true. When you decrease the temperature, you decrease entropy, right? Increasing temperature increases entropy. Decreasing temperature will decrease entropy. Okay. And, thinking about this, researchers and scientists that were the first to kind of discover and think about entropy asked the question, well, is there a temperature where all motion would cease and therefore entropy would be zero? And that happens at what you might have heard as absolute zero or 0 Kelvin. That is thought of as the temperature where we have absolutely no motion. And this idea was postulated by William Thomson, who was also known as Lord Kelvin, which is the temperature scale is named after him. Okay. And this is where the third law of thermodynamics comes in. Okay. And the third law states that the entropy of a perfect crystal is zero at absolute zero. So if you have a perfect crystal and you have it at absolute zero, it will have zero entropy. So delta S of the system, your perfect crystal is your system, would be zero at 0 degrees Kelvin. Okay. A perfect crystal really means that you have perfect alignment of all the atoms in that crystal or molecules in the crystal. At absolute zero, the particles have a minimum amount of energy, a minimum amount of kinetic energy. So in theory, you only have one microstate. And when you plug in, if you use that equation for statistical entropy and plug in one microstate for W there, ln of 1 would be 0, so your entropy would be 0. Right? In reality, we can never reach absolute zero. We can get in a laboratory setting or maybe perhaps even in deep space somewhere, you can get very, very close to it, but you really can never reach absolute zero. Okay. And the other aspect to this that you just can't obtain is a perfect crystal. There's always going to be, impurities in any crystal, discrepancies in bond lengths or sites that are unoccupied or occupied by a different molecule or atom than the rest of the crystal. So there'll always be imperfections in the crystal and you can never quite reach absolute zero. Right. So the third law by itself might not seem very useful, but the ramifications of the third law is that you can calculate absolute entropies. Okay. So the entropy of a substance at some temperature above 0 degrees Kelvin, absolute zero, right? We know the entropy at absolute zero is zero. So any temperature above that, we know that it will have a positive entropy, and we can calculate it. Right? And how do we do that? Well, to find an entropy of a substance at a given temperature, you cool it to as close to absolute zero as possible. Then you heat it in small increments. You measure the heat and the temperature, and calculate delta S for each increment. Okay, that the sum of these delta S values gives the absolute entropy at the temperature of interest. Right. You're not going to need to do this in this class. This just kind of explains how these entropies are calculated that are in tables. Right. And those values are reported as standard molar entropies, which is an S with that not superscript. Okay, that just means it's at standard conditions. Right. And it's the absolute entropy of 1 mole of a substance in its standard state at 298 degrees Kelvin and 1 bar of pressure. So let's compare energy and entropy. Okay, the total energy of the universe remains constant. Okay, that's given by the first law, right? So delta E of the system plus delta E of the surroundings, that equals delta E of the universe, and it has to be zero. Delta H, at least in chemistry, is often used to approximate delta E. For enthalpy, there's no 0 point. Okay, so we can only measure changes in enthalpy. We can't measure, a given enthalpy at a specific temperature. We can only measure a change in it from let's say a reactant to a product. The total entropy of the universe increases, so that's the second law. And we write that mathematically as delta S of the universe equals delta S of the system plus delta S of the surroundings. That has to be greater than 0. Right. For entropy, however, there is a 0 point, and therefore we can determine absolute entropy values at other temperatures. So summarizing the laws of thermodynamics, okay, first law again, energy can't be created or destroyed. The other way you can sort of put that is the energy of the universe is constant. And then also you could sort of use this term to describe that there's no such thing as a free lunch, right? For the second law is the entropy of the universe is always increasing. You can think of that in other terms like energy tends to spread out. And then if we sort of go on another path too, you can think of there's no such thing as an even value lunch. Okay, so forget free lunch, not even an even value lunch. The way I like to sort of think of entropy is like a house advantage. So in gambling, casinos have what's known as house advantage, which is a built-in odds that favor the casino in all the casino games. So in something like roulette, right, you might think if you get a buddy and go sit at a roulette table, one of you can put a bet down on the red, and another person, your friend, could put a bet down on black, and you could just sit there, each of you putting a bet on red and black, sit there and get free drinks, and when one of you wins, the other will lose, and you're going to break even, right? The house advantage, though, however, for this game, are these zeros. So eventually, the ball is going to land on a 0 or double 0, which are green. So both the bets, red and black, would lose in that case. So that's the house advantage that's built into roulette. Okay. And entropy is kind of like that in terms of thermodynamics. And then finally, our third law of thermodynamics, the entropy of a perfect crystal at absolute zero is zero. The other way you can think about this is absolute entropy varies with temperature, and we can use that to calculate. And so thought I'd play this clip because, why not?
I'm worried about the kids, homie. Lisa's becoming very obsessive. This morning, I caught her trying to dissect her own raincoat.
I know. And this perpetual motion machine she made today is a joke. It just keeps going faster and faster.
And Bart isn't doing very well either. He needs boundaries and structure. There's something about flying a kite at night that's so unwholesome. Hello, Mother dear. Oh, that's it. We have to get them back to school.
I'm with you, Marge. Lisa, get in here. In this house, we obey the laws of thermodynamics.
Okay. That's one of my favorite Simpsons quotes, at least to use in class. Right, so in this class, we will obey the laws of thermodynamics. Right. So in summary, the factors affecting entropy: volume, entropy increases as volume increases; phase of the system, entropy increases as particle motion increases; entropy also changes when solutions are formed. Right. The number of particles, or complexity of a molecule, entropy will increase as the number of particles or the complexity of a molecule increases. And finally, temperature, entropy increases as temperature increases. So we can use these observations to predict entropy changes associated with chemical reactions. Before we learn how to calculate any absolute entropies, we can use these observations to predict entropy changes. So predicting the sign of delta S for a reaction. Okay. So if the easiest example of this is if we're looking at a reaction that involves the change in number of moles, in particular of a gas. The delta S of the reaction, the entropy change of the reaction, is going to be positive if the number or amount of gas increases. So if you're looking here, right, the coefficients before the molecules of the reactants, so that'd be 1 plus 1, that's 2. And here we have a 2. So this right here, in this case, we're not, this is a solid, right? So we have 1 mole of gas of the reactant, 2 moles of gas as a product, right? So the number of moles of gas is increasing, and therefore this would have a positive delta S. Right? If that's reverse, if the amount of moles of gas is decreasing, we're going to get a negative value for delta S of the reaction. So here's an example. We have 1 mole plus 3 moles of H2, so that's 4 moles of reactant going to 2 moles of product, right? They're all gases, but we're losing number of moles of gas. So this would have a negative delta S. We could predict that. This molecule, NH3, is more complex than H2 and N2, but in this case, the number of moles, the number of gas particles actually supersedes in that complexity of each individual molecule in importance. Okay. Delta S is likely to be positive if a new structure forms that has more freedom of motion. So an example here is this very tightly bound and constrained 3-member carbon ring. when we heat that up, it opens up. This chain molecule of carbon actually has more degrees of freedom of motion than this three-member ring, so the delta S in this case would also be positive. Okay, so let's try a practice question here using these concepts, trying to predict the change in entropy for these reactions or physical changes. All right, so A, we have 1 mole of SO2 gas or 1 mole of SO3 gas. Let me get my pen. So SO3 is a more complex molecule. They're both gases, so we would go with SO3. Okay, 1 mole of CO2 solid or 1 mole of CO2 gas, right? That's a phase change. The gas is going to have a higher entropy. C, we have 3 moles of O2 or 2 moles of O3. Right? So this could be kind of a tricky one, but remember the number of moles of gas is much more important than the particular size of the molecule of gas. So 3 moles of O2 is going to be a higher entropy. 1 mole of KBr solid, potassium bromide, or 1 mole of KBr aqueous. So that would be the dissolved KBr would have a higher entropy. E, seawater at 2 degrees or 23 degrees. Right? Remember, entropy increases with temperature, so that would be 23 degrees. And finally, 1 mole of CF4 gas or 1 mole of CCl4. Right? And this is maybe the trickiest one, okay, because the molecules are basically the same, right? They have the same number of atoms in them. Well, it turns out the larger atoms you have in a molecule will lead to a larger entropy. So CCl4 will have a higher entropy than CF4 because chlorine is a bigger atom than fluorine. So the other way you can kind of think of that is chlorine, bigger atom. It has more electrons, so there's more microstates available. Okay. Practice question 2. Let's predict the sign of delta S of the system for this reaction. So delta S of the reaction. We have N2 plus 3H2 going to 2NH3, and we sort of saw this as an example earlier. Okay, is this going to have a positive or negative entropy change? Right, and again, you count up the number of moles of gas on each side. So there's 1 plus 3, so 4 moles of gas is going to 2 moles of gas. Right, so we're losing number of moles of gas total. So in this case, our entropy change of our reaction is going to be negative. And when you look that value up, it's actually negative 198.59. Okay, so it is indeed negative. Okay. Last question on predicting entropy changes. Okay, so for which reaction is delta S of the system or delta S of the reaction positive? Right, so we need to look through these. We have, and again, when you get a question like this, the first thing to do is look at the number of moles of gas on each side. Right, so for A, we have 1 plus 2, so there are 3 moles of gas going to 1 mole of gas. So delta S in that case is going to be negative. B, we have 1 mole of gas plus 1 mole of gas, so 2 moles of gas going to a solid, so 0 moles of gas on the product side. So that delta S again is going to be negative. Okay, for C, we have a solid going to 2 moles plus 1, that's 3, plus 4, So a solid going to 7 moles of gas, that is going to be greatly positive, right? And then finally, we have two aqueous things, HCl and NaOH, going to NaCl and liquid water. And in that case, maybe this one's a little bit harder to predict, but the fact that you're forming a molecule H2O instead of having OH minus ions and H plus ions floating around freely, you can sort of think that you're losing degrees of freedom there, so that would also be negative. But this one is harder to tell. Okay, so C would be the best answer for this problem. Okay. Oh, I lied. There is one more practice question. Trying to estimate entropy changes. Okay, this one's fairly easy. So you have two systems. Okay, the first one is carbon solid or carbon diamond, both solid, carbon graphite or carbon diamond, which will have the higher entropy value. Okay, we mentioned this earlier, right? And graphite was the choice. It has the higher entropy of those two, allotropes. The second pair, we have carbon monoxide or carbon dioxide. And again, carbon dioxide, they're both gases. So carbon dioxide is going to have the higher entropy because it just has one more atom in its molecule, right? So those are the pair that would have the higher entropy. So if you look at the multiple choice, that would be B. So that would be B. Okay, section 2 of chapter 20. And this is where we go through how to calculate the entropy change of a reaction. And it comes from standard molar entropies. Okay, so the standard molar entropy of a substance is measured for a substance in its standard state, and it has the units of joules per mole Kelvin. Let me get my highlighter here. Right, so the units for entropy are joules per mole Kelvin. And for enthalpies, if you remember back, those units are typically in kilojoules per mole. So here's a sort of a alert or a hint for this class. When we're moving on to the next section and talk about free energies, we're going to have to use enthalpies and entropies. Okay, just keep in mind that those units are different between the two. One's in kilojoules per mole usually, and the other's in joules per mole. So you need to you'll need to convert one to the other unit. Okay. Right, and again, standard states are shown here. I'm not going to test you on what a standard state is, so you don't really worry about that too much. But just remember that little knot, the degree thing, that superscript, that's just telling you that these are calculated at standard state. Here's a table showing some of them. Not going to have to memorize these, so don't worry about it. On questions where you need to use these, you'll be given them, like on an exam, for instance. You'll be given a table at the end of the exam, or in the problem itself, it'll give you these values. For homework, you just look it up in the appendix of the book. You probably could look these up online too for the homework, but I would suggest not doing that because they might be slightly different than the values in the back of the book. And the homework is going to want you to use the values that are in the book to get the right answer. So just be aware of that. We can see examples when we talked about the trends in entropy. We can see some examples of that here, right? So for BR2, the gas has a much higher standard molar entropy than the liquid does. Okay? And again, our allotropes of carbon, diamond here, you can see the entropy is lower than graphite. And then hydrocarbons, right, as these methane, ethane to methanol, we're getting more complex in those, at least from here to here, we're getting a little bit more complex. And then methanol, you actually have a bigger atom there, oxygen, bigger than carbon, and you can see that that entropy does increase as well. So how do we calculate entropy changes using these? And it turns out it's very similar to how we used the enthalpies of reaction to calculate, the standard enthalpies to calculate the entropy of a reaction, right? You take, if you want to find the change in entropy of a reaction, you take the sum of the molar entropies of the products minus the sum of molar entropies of the reactants. And again, the N and the M, those just represent the coefficients of all the products and reactants in the balanced chemical equation. So that's of the entropy change of the system, right? In this class, the system is going to be our chemical reaction. Okay, calculating an entropy change for the surroundings. To do that, right? Remember that you kind of need to know both, because to determine if something's spontaneous, you really need to know that the entropy of the universe is positive. So you need to know both the reaction, the system, and the surroundings. So how do we do that? Well, the heat gained or lost by the system is going to be equal and opposite to the heat gain or loss by the surroundings. So we can, I believe we mentioned this equation last lecture as well, but the entropy change of the surroundings is going to be equal to Q of the system, negative Q of the system, right? Because it's equal and opposite, divided by the temperature. And the Q of the system, the heat transferred to or from the system, that can be approximated, at least in this class, by the delta H of the reaction, right? Because it's a chemistry class, our systems are typically going to be chemical reactions. Okay. So delta S of the surroundings is going to be equal to minus Q of the system over T, which is just minus delta H of the reaction over T. Okay. So for a spontaneous process, a decrease in entropy of the system has to be outweighed by an increase in entropy of the surroundings. Okay. Thus, the surroundings function as a heat source or a heat sink, either giving up heat to the system or taking it away as needed. Okay. An exothermic process, that's where heat is given off by the system. The surroundings have to absorb that heat, right? And thus the entropy of the surroundings would increase. Okay. So you have Q of the system here would be a negative value, so Q of the surroundings has to be a positive value, and therefore delta S of the surroundings would be a positive value. Okay. Opposite is true for endothermic process. Surroundings would provide the heat absorbed by the system, and the entropy of the surroundings would therefore decrease. Okay. So the key point of this slide I really wanted to point out again was that the heat of the system is equal to negative heat of the surroundings. Okay, so just remember that equal and opposite sort of nature to those. And then again, that equation for delta S of the surroundings is equal to minus delta H of our reaction divided by T. Okay, technically this is for a process at constant pressure, but we're just going, for this class, assume that always holds true. Okay, so let's have a practice calculating some delta S values. Okay, so calculate the delta S for the formation of 1 mole of HI gas from its elements given the following information. Let me get my pen. Okay, so first thing here, we need to write down what reaction is actually occurring. So the reaction here, we would have so our reaction would be hydrogen gas plus iodine gas, which would be I2, goes to HI. And to make this the stoichiometry here the same, balance the equation, you'd have to have the coefficient of 1/2 out in front of both of these, right? Because we're forming 1 mole of our product. Okay. You could put 1s out in front of H2 and I2, but then you'd have to have a 2 in front of HI. So because the question says 1 mole, we'll just go with this. When you calculate the entropy, it really shouldn't matter either way. Okay. So again, we're going to use our equation for delta S. It's going to be the sum of the molar entropies of the products minus the sum of molar entropies of the reactants. So what are the products? Well, there's only one product. It's HI. So that's pretty easy. The coefficient is a 1, so we just have 1 mole times that entropy value, which is given here as 206 joules per mole. Just include those units. Joules per mole Kelvin. Right, you'll notice that the moles will cancel out, and our answer will be in joules per mole. So then we minus the sum of the reactants, and we have H2 and I2. So there'll be coefficient of 1/2 mole for H2, and the molar entropy is 131 joules per mole Kelvin, plus 1/2 mole times the molar entropy of I2, which is 116. Okay. And when we do all of that math, the delta S value will be 82.5 joules per Kelvin. Okay. Okay, final question, calculate delta S, and this kind of is a question that will be using things we've learned from the past 2 lectures together. Using the values below, calculate the standard entropy and enthalpy changes for the reaction 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. Okay, so this is a combustion reaction of ethane. Okay, so our standard molar enthalpies and entropies, and enthalpies of formation are given. Okay, and remember, we have the equation for delta S of the surroundings given here as well, which we'll need. Okay. Is the reaction endothermic or exothermic? What is the enthalpy change of the surroundings at 25 degrees Celsius? And is this reaction spontaneous? Okay, so let's work on this. So let's do enthalpy first. So calculating the enthalpy, it's going to be the products minus the reactants. And I'm going to sort of not include the units in this just to save space. But remember, a good rule of thumb is to always include them when you're doing this, especially on an exam. So we have 4 moles of CO2, and its enthalpy is given there, enthalpy of formation. 6 moles of H2O with the given enthalpy of formation, 285.8. Right, so that'd be our products minus our reactants. So we have 2 moles of ethane at negative 84.7 kilojoules per mole, plus 7 moles of O2, which has a enthalpy of formation of 0. So that one kind of just doesn't factor in. So when you do all that math, you get negative 3,119.4 kilojoules per mole. So is this exothermic or endothermic? Well, it's exothermic because that value is negative. Okay. So that means that reaction's giving off heat to the surroundings. Okay, now let's calculate our entropy change, delta S. Again, you do the same process, but now we're using our molar entropy values. Right, so 4 moles times 213.8 joules per mole Kelvin, plus 6 moles times 69.9 minus 2 moles times 229.5 plus 7 moles times 205. So that's one of the differences between enthalpies and entropies. Enthalpies, things like O2 will have a 0 for its enthalpy of formation, but you don't get those 0 values ever for your standard molar entropies. So it's maybe a little bit more work to calculate. So delta S of this reaction, or our system, is negative 619.4 joules per Kelvin. All right. So now we need to answer, if we look back here, right, we've answered, is the reaction endothermic or exothermic? All right, we've calculated standard entropy and enthalpy changes for both. Now we need to answer what is the enthalpy change of the surroundings, and then finally, is this reaction spontaneous? So the enthalpy change of the surroundings, and I should denote this was the reaction or the system. Okay, so the surroundings, we're going to use that equation up top, and it's going to be minus Q of the system over temperature, right? And that Q of the system is just going to be minus delta H of the reaction, again divided by the temperature. Okay, so the delta H of our reaction here is negative 3,119.4 kilojoules per mole. And what's the temperature? The temperature is, and I'm sorry, the units here are in kilojoules for that entropy because we are multiplying through by moles. So those units are just kilojoules. And we're dividing by the temperature. And it said on the previous slide, we're at 25 degrees Celsius. Okay. We need to convert this to Kelvin so we can compare it to our entropy that has Kelvin in the units. So 25 degrees Celsius plus 273, that converts Celsius to Kelvin, so that'd be 298 Kelvin. Right, so when you do that math, you should get a positive value, something like 10.467 kilojoules per Kelvin. Right. And now we're trying to answer this question, is this spontaneous? So to do that, you would look at the sign of delta S of the universe, right? And that's going to be delta S of the system plus delta S of the surroundings. So our system has a delta S of negative 619.4 joules per Kelvin. And the surroundings, this is in kilojoules, so we need to convert that to joules to be able to add it together. So it's actually going to be 1,000 times that, so it'd be 10,467 joules per Kelvin. Right, so you can see that that positive value for delta S of the surroundings outweighs the negative value for delta S of the system. So our delta S of the universe is 9,848 joules per Kelvin. Okay, that is greater than 0. Therefore, this is a spontaneous process. Okay. So next time we'll cover the third and final section in chapter 20, covering Gibbs free energy. And this is sort of a reprise of how do we know when a reaction will be spontaneous. And we'll also cover a little bit of material from chapter 12 talking about some important intermolecular forces.